Good afternoon. This is Group 14, and our project proposal is on distributed processing of Go's GLM Lightning data across critical operational domains. The team members are Derek Saunders, Timothy Azenord, Christian Jones, Tomiwa, and Kaylana Brooks.
The motivation for our project is to discuss how the GLM provides continuous high frequency lightning observations. We'll also be discussing the many sectors that depend on lightning analytics for safety and planning. And we'll be looking at the GLM data volume and how it is extremely large and thus requires distributed systems. The overall goal is to evaluate how different architectures support domain specific workloads.
So what is GOES GLM? It is a space-based lightning detector on GOES 1617, and it captures optical lightning events every 20 seconds. It has a high spatial and temporal resolution, and it is an ideal data set for data-intensive computing research.
So for some of the storage formats we're going to be using, the primary one is going to be raw net CDF and HDFS, as well as HBase. And some of the processing frameworks that we're going to anticipate using is Apache Spark for our distributed analytics, as well as implementing some time-based spatial partitioning strategies. So the first thing we're going to take a look at is power grid infrastructure. Um,
Wait, before we get that, just a quick breakdown of all the workloads. We have five operational domains in power grid infrastructure, aviation operations, satellite and telecommunications, severe weather forecasting, and climate and atmospheric research.
Yes. So for our first investigation, we have our power grid infrastructure. And kind of the motivation behind this is that lightning strikes are a major cause of power outages, and they equip damage and cause grid instability. And we need utilities that have near real-time awareness of lightning near transmission corridors. So my part of the presentation would essentially simulate how a utility company would monitor lightning near power lines. And some of the things we like to touch on for this is why lightning matters to grid reliability, which format handles spatial filtering best, and what kind of bottlenecks appeared when tackling this problem.
And the next area of focus is aviation operations. So the motivation for this is that lightning near airports affects takeoff and landing safety, ground crew operations, and flight routing. Aviation requires low latency, high frequency lightning awareness. So my workload will simulate lightning proximity detection around airports, and the query pattern I'll be using is point buffer spatial queries for low latency filtering, and this will result in cache spark queries outperforming repeated raw HDFS scans.
And with satellite and telecommunications, the motivation and purpose is that lightning near uplink and downlink facilities can disrupt communications, damage equipment, and degrade signal quality. These operators that work in these facilities need to know the targeted hazard detections that comes with lightning storms and activity. The workload for this will simulate lightning detection near satellite ground stations, which hopefully gives us a focus on why lightning affects satellite telecom operations, how small region filtering differs from large scans, why HBase excels for small selective queries, and when Parquet becomes more efficient.
The next focus of the project is the severe weather forecasting. The motivation behind this is how rapid increases in lightning activity can often signal storm intensification. Meteorologists can use lightning trends to detect developing severe weather patterns. In the end, we're going to test across 5-minute windows and aggregate the data of lightning strikes in those windows. The direction will lead us to simulating flash rate increases in detection using sliding time windows.
The final domain that we'll be looking at is the climate/atmospheric research domain. The purpose for that will be to study how climate scientists study long-term lightning patterns to understand seasonal cycles, convective behavior, and climate variability. The workload for this domain will simulate monthly lightning climatology, which should help us answer why lightning climatology matters, how monthly aggregation works, why Parquet is fastest for large scans, and why net CDF is slowest for full file scans with no indexing. The cross-domain findings will simmer down to no single architecture is best for all workloads, as we will discuss further with the multi-domain parquets that are best for large scans and aggregations, and why HBase is best for selective small region queries. And then finally, we'll touch on raw net CDF consisting of the slowest data aggregation. Partitioning strategy strongly affects performance, as we will see that the different domains require different data sets and analysis.